Also, just so you know, I don't know your physics, right? But I want to do one of these at some point, and so your talk is my entire basis for it.
My talk spaces is Tonkun's talk. So, you know, it all, you know. Well,
Thank you, Tonkun.
yeah, exactly. Thank you, Tonkun.
On diamond color centers.
That'll be it.
Do you know if you can do like what you did in undergrad? Or is it what you did for PhD?
Please go get pizza and also please sign into the talk by scanning that QR code. So that people know that pizza to real pizza. You know.
It wasn't embezzled.
Exactly, right.
It wasn't embezzled.
When the department does their pizza audit, they wanna know.
They want to know. No pepperoni was put on that pizza. Smartphone beam.
You want any pizza? We can set some
I'll
aside
have
for
some.
you.
Yeah. Oh, is it gonna get? Is it gonna get
It
demolished?
might all get eaten. Yeah, you can go
Just
just.
nice.
Feel free to jump the line.
Nice pepperoni pizza. Yeah, jump the line.
Yeah.
Yeah, you can back up there.
I need to be back up there right now.
Exactly.
And I'm already in line, so.
Very long.
Some of your VIP, once you grab.
I don't make the rules, I just follow them. That's not. I want back there. First executive order, presidents have to follow the law.
Oh, yeah.
Yeah, that's surprising. You sleep, right?
Yeah.
Now you would have to.
Yeah, I've only been up there like. It's not the very first in the school. I started off exploring. What's that? I think so. I mean, what's you can do something. It's like, oh, yeah, there are.
When I go like, any clickable.
Making cool.
So like, are you making? I heard that while I was looking.
So, yeah, there's some good. Yeah.
We have next one.
So, sufficient amount of people like it.
Or like once I'm like established and have other
Shows lots.
That's lovely. I haven't done much. I know I can.
All right, While the last few people are getting pizza here, I'm gonna do my CU Prime spiel. So CU Prime is a student organization, mostly grad students, although we absolutely welcome undergrads to get involved. And our goal is to create an inclusive community in the physics department. So we do that in a few ways. One of them is this talk series. We also have a coffee hour every Monday from 11:30 to 12:30. And we are reviving a mentorship program. So if that's something you're interested in, kind of being paired with a group of lower division undergrads and upper division undergrads and grad students in like little cohorts, so you can all talk about your struggle in physics. If that sounds interesting, make sure to get on the C prime announce list because information about that will be coming out in the next week or two. So with that, please sign in here if you have not already. And also,
And this 1,400 students, they should sign in on your iPad or app as well as on the front end.
yeah, clickers or something, in this 1,400, I don't know how that works. But let's please all welcome Jack Doyle to tell us about nuclear clocks.
Well, thank you, CU Prime, for having me. It's a pretty big honor to be able to get to do talk like this, and it's every experimentalist dream to just talk about what they do for research. So, thank you very much. So I guess let's start with a little about me. So, I am probably the luckiest person on earth. I got to spend about half of my life up till high school living in Japan. So I went to some Japanese middle school and some Japanese elementary school. In high school, I started doing first robotics. How many first robotics? Yeah. Oh, we got a few. All right, nice. It's nice to see. So nice to see those people. The team. I started the team in 2017, and then it's still thriving, as you can see in the photo on the right. And I don't know, and maybe there's some people that recognize him, but not certainly not from this photo. But is Marcus Greiner? It's actually hiding back there in the team. So it's some very famous whole molecule physicist. So it's a little fun little connection. For college, I started out at the University of Wisconsin-Madison for mechanical engineering. And then after about a year, I was like, okay, actually, I want to do EE. And so I did electrical engineering for a little bit. And then right during COVID, I transferred from University of Wisconsin to CU for EE. And then I did, CU and EE, and I did physics for about 3 years here. And when I first signed on, it was the middle of COVID. So I wanted to work in a lab. I knew that from working in Wisconsin. I worked in a great lab in Wisconsin, Jennifer Choi's lab. And I knew I wanted to continue working in physics. And so I just emailed like everyone. I emailed everyone that worked in JILA, and I emailed everyone in the engineering department. I was like, please, I'll do anything. I'll do literally anything. Just, hire me for the summer at least. And June emailed me back. And it was like, what do you want to work on? So that's like insanely lucky moment number one. That someone's willing to pick you up and take kind of a high risk, which is just this person just transferring such. So June does a lot of research, a lot. And so research areas, this is on his webpage, is ultra-cold strontium, precision measurement, and then ultra-cold molecules. There's like 2 ultra-cold molecule experiments, 3.5 ultra-cold strontium experiments, and 3.5 precision measurement experiments. So it's a pretty chock full lab, and I see quite a few members in the audience. I wanted to do this one, and he was like, okay, do you want to do breath analysis with this comb? You want to do carbon 60 buckyballs, which are these kind of little molecules that are made out of carbon? Or do you want to do extreme ultraviolet frequency combs for a nuclear clock? And I was like, extreme. I like the word extreme. So that's how I selected what I would be doing. I guess for the last 3 years and now for the next 6 or 7 years. So to start the physics talk, this is the title. It's Going Nuclear with Ultraviolet Lasers, Optical Nuclear Clock, which is a pretty, kind of seems like a pretty hard to manage title until you just realize that you can just call it clock. We are just making a clock like any other clock. And I'd like to motivate some of the reasons we would make another clock. But how I'm gonna approach this talk is I'm going to talk about clocks, and I'm going to talk about why you would kind of care about specifically a thorium clock. I'm not loud enough? Okay, sounds good. So we'll do a nuclear clock project overview. And I'd like to start by listing some clocks. It's a very basic starting. So introduce yourself, talk to your neighbor. Y'all probably know each other, but introduce yourself and just think about clocks. Like no high level stuff, just think about clocks. What kind of clocks could exist, what do exist, and how do they work? Just for like a minute, maybe.
Like how you have the monitor, right?
Yeah, so like the sun, you got the sun, that's a clock.
Where like if you take all the numbers around the clock and you add a clock, it adds up to like, sorry, the average is always the same. Like you go across the clock.
Nature watch out.
Like, yeah.
You got the satellite. What's the satellite doing, right? 10 to the -7, 17 sundial. Got a pretty nice sundial you got there.
There's spark clock theories. I think are you doing
All right. So I'm sure y'all came up with some good clock ideas. I'm going to introduce a few. It may have shown up in your discussions, but before that, I'm going to talk about. Okay, so again, I was in EE. I graduated in EE. So the learning style in EE is a little bit different than it is in physics. In physics, they're like, okay, we're going to start with like Maxwell's, and we're going to rigorously define everything. We're going to go build up from the basics. Engineering lectures work a little different. They're like, okay, here's a super high level concept. I'm going to kind of convince you with examples that there's a really good reason you should use this high level concept. So that's all I know how to do. So that's what I'm going to do. And my high level concept for you today is a clock is comprised of an oscillator and a discipline. And if you have those two, you have a clock. So for example, so I had a bet going on. Does anyone know who this is? I have lost money. That is Robert Fripp, famous bass player, but he's really good and he knows how to play very consistent notes. And so let's imagine Robert Fripp plucks his guitar string and it oscillates. We'll call that our oscillator. And when Robert Fripp plucks his guitar string and listens to it, he's very good at saying, that is too high pitch. I'm gonna go down to I'm gonna change how I pluck to go to the exact note that I want to play. And coincidentally, one of his albums is called Discipline. So I don't know, music nerd bit, but that's okay. So that's the high level concept I'd like to kind of get everyone to think about today is oscillator and discipline. So let's start with, I guess, the motivation for building a better clock. I have a graph here, and this graph is fractional frequency stability and frequency. So those, two are a little hard to manage at the beginning, but how many people kind of have an idea of what a frequency is? Everyone, nice. So, okay, what is the resolution of the clock? It's like, okay, I can't, measure a pendulum, swinging back and forth really well by looking at the sun. You need some sort of level of high frequency component to measure some certain things. And for fractional frequency stability, I have, how reliable is the clock? how reliable is it that I can say this clock is at this frequency? How reliable? So you see here, I have a little thing stolen from Wikipedia. It's a pendulum and it's swinging. I haven't taken the undergrad lab here. How many people like have like a timer and they time like a pendulum and they like say like, oh, what's the period based on the mass and the length of the thing? No. Hey, there's one. It's from Tsinghua. So I guess not in CU, but okay, that should be a lab because it's good. I can't measure that with a sundial. But this is in the George Gamow Tower, you have this kind of clock. And it's a little hard to think of which one is the oscillator and which one is the discipline in this one. Next example for the quartz crystal clock might be a little bit more clear as to differentiate the two, but we'll have to talk about one. So how many people know what these things that I have on the symbols I have right here are? You got one. Okay, so two. Okay, so this U1 thing is called an inverter, and it takes what's on its input and it puts the opposite on its output. And so I'd first like people to think about what would this do? If I just connected an inverter, its input to its output, what would happen? We got someone doing this. We got any other opinions on what it would do? That's one correct answer. There's another correct answer. All right, the second answer is it just goes nuts. It kind of does whatever it wants to do. So it kind of doesn't really enjoy its situation, and it just kind of outputs spam white noise. Whoops. What this is I would like to argue, at least, that this is an oscillator. This part of our clock here is an oscillator. And its discipline is this crystal right here. I guess if we haven't seen these symbols, I'm just going to breeze over it. But this quartz crystal clock, that's how your phone keeps track of what it's doing all the time. It's also how I guess most electronics have this exact circuit in it, where you have something that gives the opposite of its input, and you connect it to a little crystal, a little piece of quartz or ceramic. And you can see kind of up in here, I've been tracking the behavior of the system here. So we have the pendulum angle oscillates in time. It's pendulum angle theta oscillates in time. For the quartz crystal clock, the output voltage oscillates in time. And then we can kind of go to some other microwave clocks. There's someone in the audience who does microwave clocks. No? Okay. Microwave clock is the electron hyperfine interaction changing over time. And then down here in the optical atomic clocks, we have the electric energy level changing over time. So, and you can see that the time scale has changed for each one of these. So seconds for the pendulum clock, microseconds for the quartz crystal clock, nanoseconds for the microwave clock, and then around femtoseconds for the optical atomic clock. So all that's saying is as we go to the right, we have been increasing in frequency for all of these clocks. And I won't argue it, I'll just tell you that the fractional frequency stability has been getting better. So 10 to the minus 10 is fractional frequency stability. So that's very low error, let's say. So here's kind of what the periods of these systems generally depend on. So I guess I'd like to ask everyone, how would these constants vary? So this is another talk to your neighbor one. I forgot to put this in a blue box, but talk to your neighbor, how would these constants vary to change the period of your oscillator? So the period of oscillation of our pendulum clock is 2 pi times the length of the pendulum over oops, that shouldn't be capital G, my bad. Earth's gravity, which is little g. So have a discussion as to how these could possibly vary.
Sort of pendulum. Unless it's like
Yeah. Share your knowledge.
if it's like really, 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 really long, it's gravity bodies. I don't know, maybe we can put it in the international space station. Yeah.
So what would make the length increase? Yeah, what would make the length increase? Make the string longer, but let's say I want to make it very consistent, and so I just use one string. Is there any way that the length could increase by some other mechanism? Different tensions, so maybe it like breaks over time and increases its length. What if it like heats up and the fine material of the pendulum expands? There's a few ways you can get energy.
So. Not really. If I had a wire and some electricity, I can have parallel plates. And then there's charge taken up on this one, and then it has to go on as the other one, and then I get the same. So it's going in the electron. Inductance is when we take advantage of like magnetic field projects, and we actually get it to stop instantaneously, and then that starts. Yeah, I always have a problem. It like. Yeah.
All right. So can I get some opinions for how all of these would change? Is there any ones that are like people don't know? I don't know what that is. Everyone knows everyone. Which one?
Magnetic moments.
Magnetic moments. You like asking.
I have no idea what it is.
So imagine I got a little nucleus. There's a little bar magnet in there. It's a magnetic moment.
How does that change?
How does that change?
How can you like affect that?
How can you affect that? Yeah, it's a good question.
Nice.
How would you affect the magnetic moment of a nucleus? Yeah, it's a great question. Does it? Does it change? What about the stuff on the right, like charge on the electron? Does that one change? Does it? Was there a hopefully not? Was there like a hopefully not? Did I hear a hopefully not? That's pretty good. Yeah, hopefully not too much. But yeah, I think. What about the length of a pendulum? How could that change? We got a little someone doing this. What? Wind up like yo-yo.
Yeah.
Maybe. I don't know. I don't know where the yo-yo is or what might wind up. Yo-yo is a pendulum. The what?
Oh, you're saying, right, repeatedly the screen like it, like.
Oh, okay. I see. So if it goes around, it goes around. Yeah, it could do that. It could do that. I would hope that the conclusion was, and would like to at least argue that the stuff to the left here, it's easier to vary. If I have like a little string, if I heat up the string, its length is going to change. G changes from this room right here down to like the first floor. We know that from, because you can measure it. Capacitance of crystal, inductance of crystal, all these completely depend on temperature. So if my crystal expands, now the properties of that crystal are different, and the oscillating frequency is totally different. How does mu n mu e change? Does it? I don't know. And then the one on the right, like E naught h bar, charge on the electron. I mean, hopefully those don't change too much. Right. So I guess hopefully I've created some at least fake intrigue for kind of clocks and their makeup of oscillator and discipline. So what is a nuclear clock? Which is, kind of going back to the title and looking at making a nuclear clock, and how would one build a nuclear clock? So if I did my job right, you kind of look at this and you say, okay, at least this guy is arguing that this is disciplining my oscillator. My electronic transition, if we go back to wrong direction, spoilers. If we go back to the optical atomic clocks, my discipline was my electronic levels of my atom. And so that was my discipline. And if you believe that, okay, I've done my job. Nuclear transitions are surprisingly similar. So, you look at the orbits of the electron around your atom, and you can drive transitions from one to another with lasers and such. Nuclear transitions are very, very similar. But notice this one says 1 eV, and this one says 1 MeV. So 1 mega electron volt, so 1,000,000 times more energy. Who here has seen an electron volt ever appear in anything? No, I mean, that's a hard question. No, like in a physics class. All right, cool. Yeah. So electron volt is a measure of energy. And the title of my slide is E equals h bar omega, and then C equals F lambda. These are two, S tier equations. You can use them, you can use them anytime. They're great. And it's basically saying like, okay, if I have an energy difference here, that's my E, then I can drive that with h bar, which is a, yes.
Very different with the H from the previous slide and this H with a slash through it.
Yes. So the H from the previous slide is 2 pi times the h bar. So, they're basically the same, but I kind of just sloppy, my bad. So yeah, and then so that defines a certain frequency that's kind of characteristic to this excited state and ground state. And then I can go even further. So this omega is 2 pi times f. So it's basically f. And then I can determine a wavelength because I have a c, the speed of light. So all of this is to say, there's going to be a lot of interchange in using frequency, wavelength, and energy. But they're all pretty similar. Cool. And so we can kind of look at this electronic transition, nuclear transition comparison and say, 1 mega electron volt, that's pretty high. That's going to be 300 times 10 to the 18 hertz. That's a lot of hertz. Compared to, 30 times 10 to the 12 hertz. That's not very many hertz. So we, I know I've messed up because my senior grad student is pondering himself in the background. Uh-oh, I think it's right. Anyway, so if we kind of look at these, they're pretty similar. And so I can kind of make the argument to you, if you accepted that my atomic transitions were a good discipline, I would like you to accept that the nuclear transition could function as one too. These electronic transitions, we said, okay, 1 eV. You can get that, 1 eV photons, you can get that with tabletop lasers, like you can buy them. For these mega electron volt level transitions that are inside the nucleus, you need higher energy photons, which is higher frequency photons. So one way to get like this kind of insanely high frequency photon is by going to a synchrotron, which is this giant facility that consumes a ton of power and gives you a laser. But it's Yes,
What facility is that?
that's Spring 8 over in Japan. So Spring 8, I guess they did some, I guess they're on here because they were relevant to an experiment that was relevant to ours. Just kind of a random one we chose. But it would be nice if I were, to not use this synchrotron light for the reason that it's not as clean, I'll say, as lasers that you can make in the lab on the tabletop. At least it's very hard to generate that. So we would like to do it with this red arrow is we'd like to excite the nucleus with coherent laser light from on your tabletop. But as with everything, there is a problem. I mentioned mega electron volt energies. Well, having like a laser at that frequency, at a super high frequency, is really, really hard to make. Additionally, there's only one that is low enough, this one right here, that you can actually kind of dream of exciting it. So this plot here, let's, I guess, break it down a little bit. So this is half-life in seconds. This is if I energize my low state to high state, and how long is it going to stick up there? And to the left here, we have energy. So how high a frequency, how high energy photon am I going to need to excite this transition? So I guess, yeah, this is kind of a comparison slide. So we're looking at electronic transitions. So this was like the electron outer shell moving around. There's all these little red dots. All these little blue dots are actual nuclei gaining energy and then losing it. So how long does those states live? Yeah.
So I've heard half-life referred to before for like radioactive decay.
Yes.
That like things have a half-life.
Yep.
Of, well, a million years or like 1 second or this sort of thing.
Yeah.
And now you're talking about like the energy in your nucleus staying there.
Yeah.
Is the half-life? Is that the same thing? Like, does losing the energy like decay your atom to the other atom? Like, is that emitting radioactivity?
So yes, there's 3 kinds of nuclear decay. So there's beta decay, alpha decay, and then gamma decay. Gamma decay is your nucleus is in an excited state, and then you just emit a photon. So this is, you can kind of consider this nuclear transition, this nuclear isomer transition, as the same as a gamma ray. Yes, sorry, is there isomer on this?
Yeah.
My bad. Yeah, nuclear isomers, yes. So these kind of these states that you can excite with a laser, we call isomers. Sorry, didn't catch that. Yeah. And there's only really one that's low enough energy that you can dream of hitting it with a laser. That's why there's this little M right here for the isomer. There's one that's kind of low, this thorium-235 M. Can anyone make a guess based on just this graph as to why that would not be a really good clock? Or in other words, like if I wanted to excite that transition, what problem would I have? This is kind of a hard question. Maybe I shouldn't ask it. I don't know. Sorry? Actually, that's a good point. Yeah. 235 is, yeah, good point. That's one of them. Exactly. If I excite it with a laser, how do I know that I've excited it? Because it just stays there. I can't actually watch it decay.
Like, yeah, how do you find it?
How do you find it? You can't find it. It's just going to be excited for like 10 to the 20, 10 to the 23 seconds. Like I don't got time for that. Also, and like to speak on like how rare the single low enough that we can excite it with lasers, but still a nuclear transition. These are like all the isotopes. There's only one, which is this thorium-229. 229 is an isotope of thorium. So isotope is like, okay, I have a certain number of protons, and that defines what element I am. But then I have a certain number of neutrons that defines, based on that element, what isotope I am. And so there's only one isotope that we currently know of that has a low enough energy that we can actually excite. And so it's expensive. It's radioactive and expensive. So I think you can really only get it from, okay, how we have gotten ours is we depend upon this kind of chance, super lucky thing that happened where one of the kind of more senior scientists at a national lab just decided, you know, we got all these nuclear bombs lying around. What if I melted them down and extracted this one isotope? Like, we depend upon that kind of just boredom, ingeniousness. I don't know. Divine inspiration from that guy to just isolate this compound for us. It was studied before this, but you know, to actually get enough to work with, we thank that guy. And so, you know, I put a lot of dollar signs. It's because it's really expensive. So how much do we want to guess something that is expensive for a physicist is? Like, I guess in units of dollars per gram, let's say. $1 million per gram. More expensive. Yeah.
Like order of magnitude or like.
Whichever you want, my guy. It's 50K per milligram. So you get like a milligram of it, and that's 50K. And if you ask again, like, hey, we want another milligram, they're like 150K. And you're like, okay, I guess not. So there's not very much of it because there was this crazy guy that, you know, isolated it for us, and it's really expensive. So, you know, I'm hoping and praying that they decide to melt down more nuclear bombs. I don't know, find a different way. Second part of this kind of problem is problems with this nuclear clock is as you kind of go to the bottom right. So your clock increases in frequency and then gets more and more stable. You can kind of tell by how lazy I've gotten in labeling the actual period. So period of pendulum, you look it up on Wikipedia. Period of crystal quartz oscillator, you look it up on Wikipedia. This one's, you know, yeah, it depends on some angular momentums and stuff. Don't really feel like writing it all out. I give up. It's a function of them. So as I kind of get lazier going to the right, it's kind of maybe I'm hyping myself up too much, but a profound statement that as you go farther to the right and farther down, it's actually harder to calculate. There's more things that are complex, more things that actually come into your system and start messing with you. So kind of, if I wanted to say, like, sit down with pen and paper, can I calculate exactly what energy the thorium nuclear transition is? Like, we don't, spoilers. We don't know. Like, there's this box, right? We at this point, we don't know like what the frequency is, what the energy is exactly. And so, as you know, if you wanted to sit down with pen and paper and calculate it, you can't really do it very well. And so everyone is just trying to say, okay, we can't calculate with pen and paper. Let's just try to excite it and see if we, you know, if I scan my laser, if I change my frequency as I'm going across my thorium, as I'm like scanning my thorium, changing my frequency, will I see it eventually? Will I see some nuclear excitations? So this is pre-2023. Our x-axis is experimental measurements. So just no time scale. It's technically time, but you know, just sequentially. And transition energy. So like what frequency energy does this discipline want to be oscillated at in terms of energy? And so it's pretty big error bars. So we have 100 terahertz uncertainty. That's pretty big. Then, and I suppose I should mention, there's a ton of ways of trying to measure this transition energy. So one way I can do it is I can get some excited isotope of something, and it decays into two like products. And one of them may happen to be thorium-229 in the excited state. Then all I need to do is wait for that to decay and look at my photon and say, okay, if I look at my photon and I say, how energetic is this photon? Then I get a good measure of how high energy this was. So this is just like looking at photons and seeing how energetic they are. Then the first observation of radiative decay photons. This is you make like a beam and it decays into thorium and you kind of observe it again. So this is still looking at the energy of the photons. And then people finally excited in a laser. Let's see, this is 2024. Yeah, 2024. And you get these kind of two kind of really close together papers finding it. And here's one from one of them. So you can see it's kind of a confusing one. I have frequency offset gigahertz and I have wavelength, and they're kind of on top of each other, but this is a little annoying maybe, because you can see this number and then you say, okay, this wavelength is in nanometers, so it's an energy, right? Cool. And this is in gigahertz, also energy, frequency. Wavelength and frequency are energy. So what they did is they scanned across this with their laser and they measured these kind of two lines. So you see the arrow pointing this way. So they scan this way, they increase their frequency. Increase their frequency. Yeah, increase their frequency. And then they did the same scan going back, decrease their frequency. And they see these two little bumps, which is their kind of evidence for seeing nuclear excitation. And this was wavelength-based calibration. So they measured the wavelength of this output and got those numbers. So how did we solve it? So what did we actually do? So this is all like, stuff that people before us have done. But what did we do? Who here has seen a Fourier transform? I want to look at the middle two rows here. There's too many grad students separating them. How many people have seen a Fourier transform? No one. Okay. So a Fourier transform is a very, very useful, and you'll see it a lot. And it basically says, okay, if I have some function of time, I can also plot that same exact phenomenon as a function of frequency, and I don't really lose anything. How chill are we with that? It's a little deep. It's a little complex. But if you think about the fact that frequency is 1 over time, maybe you believe it a bit more. But you will learn these. They will be drilled into your head. There are properties of a Fourier transform. And one of them is that if I have like a very short pulse in time, so I have some function that's like in time, in frequency domain, so this is like low frequency and high frequency, let's say, it'll also look like. And so I'm going to kind of go through some slides, and I want you to just kind of trust me that this is how Fourier transforms work. So if I have a pulse like this in time, and I put another one next to it in time, so I don't, I have two pulses. Wow, no, go back. All right, I messed up my slides, my bad. It was supposed to have two pulses and show that you get kind of some sort of spectral features in this, and then, okay, spoilers, if you have like a bunch of pulses that are very, very well defined in time, you get these spikes in frequency. So frequency is energy. So keep that in mind as we kind of go through what we're going to do for our oscillator. So yeah, and you can calculate certain properties of the spacing between these lines and the spacing between these pulses. Second one, I'm just going to breeze through this one. This one's called high harmonic generation. The Captain Marine group does a bunch of this, so you can go talk to them if you want to know more. I only have like the most basic level understanding of it, and I just use it. So the low level users explanation of it is 7 photons go in, 1 photon of 7 times the energy comes out. So obeys conservation of energy, so maybe easy to believe. But this is also saying that, okay, if I have a certain frequency going in to my little gas target here, then 7 times that frequency comes out. So this won the Nobel Prize in 2023. And this comb thing won the Nobel Prize in 2006 or 5. It says 5. I thought it was 6. It's my bad. This guy was at JILA. The hometown guy. So these are kind of 2 pretty complex things I've just kind of thrown at you. And I don't know if you believe either of them yet. I won't be able to explain the one on the right, but this one is really, really important. The whole Fourier transform thing is really, really important. So discuss with your neighbor. Just if you have like a burning question about Fourier transforms, ask it to your neighbor and then kind of maybe talk about it with each other and see if you can come to some sort of understanding of these different phenomena about the Fourier transform.
That's so smart. It's like like probably like how many photons.
Yeah. So in this one, it's electric field, which is basically how many photons. And then the y-axis on the bottom, I don't know. It's like kind of an intensity. So yeah.
But you can see it pretty much that's definitely but it's because it's different y-axis.
Yeah, there's not only different y-axes, but the Fourier transform itself is a very kind of a complex function. It's an integral of so if I have an integral over time, and I integrate this function, so like this purple line, with respect to e to the I omega t. I integrate that, then I get a new function in that function space. And it is like possibly the most useful transform, it's called, the most useful transform you can make. You learn it. I don't know if when you learn it, if you're in undergrad physics. If you're in EE, you learn it your second year. So it's like the bread and butter of EE. EE just loves it. Sorry? You might what? It's nice for experiments.
I was explaining my motivation. You can do it beautifully.
Mongolian throat singers have taken over my presentation. There's a lot of Mongolian throat singers in our program.
Yeah, that's beautiful.
Oh, an entire 2 of them.
I would say I will never understand Fourier phenomena. It's like, cool, this is a Fourier transform of my conversation.
All right. So are there any like burning questions that you've kind of come up with your neighbor about Fourier transforms?
Yeah. But this
Yes. Sorry, can we he's asking a question. Sorry, can you ask that again? My bad. It affects it a lot. So then to answer that, you would kind of go into a linear systems class. The answer is that when I talk about taking a Fourier transform, obviously you can't integrate. So let's start with this. So the Fourier transform is, if this purple line is, for example, the y-axis is electric field, and x-axis is time. I would, if I were to do a Fourier transform of this, I would integrate this purple line with e to the I omega t over all time. But you can't do that because I guess the laser's not on for all time. That would be a little weird. So usually when people say they're taking a Fourier transform, it's you're integrating from some time to another time, and you're saying good enough. And usually it is good enough, but you know, that's a very, very, very good point. It's yeah, there's a lot of deep answers to that question. Yeah. So in our experiment, we say, okay, we're pulsing our laser at around 75 megahertz. So that's 75 million times a second. That's a lot of times a second. And so if I kind of look very broadly, if I, you know, look over some certain period, like a second, and I integrate over a second, that's a pretty good, you take the Fourier transform, that's a pretty good read on what it looks like in frequency space. Yes. Yes.
So with your omega, are you saying that to be like the?
So with my what?
With your omega and your Fourier transform, are you saying that that's your wavelengths?
So you're going from the x-axis being time to the x-axis is now being omega. So you're taking a function of time and transforming it into a function of omega. So that's a kind of an interesting thing to do. But that's how the omega factors in. And you can kind of think of it as like, when I'm integrating, I'm saying, how much does my function overlap with e to the I omega? But I'm integrating over, I'm sorry, e to the I omega t. So integrating over time. So you're kind of looking at how well each omega matches your function of time. Does that answer the question? Okay. No other questions? Yes.
A Fourier transform is usually solved numerically or like.
That's a good question. One would like to solve them closed form, but usually you don't have that convenience. Usually you're kind of looking locally at your Fourier transform and saying, okay, in the past, you know, minute, in the past second, in the past microsecond, what is the Fourier transform of my electric field? So in that case, you're doing it in a computer and you're doing a discrete Fourier transform, which is now your omega. I should have put the equation up here. The omega is like, you know, has discrete values, but you can do a Fourier transform over some certain amount of time where it's continuous, where omega is continuous. And then you can do over all time where it's continuous. So a lot of different ways of approaching it. But you can do both.
I was gonna ask just like, what is e doing?
E to the I, is it I or negative I? Does anyone remember?
It doesn't, one of them is gonna be the polar Fourier transform, the other one is the inverse.
Yeah, but I don't remember which one is which.
I think.
Inverse is the negative. Okay, so e to the I omega t is an oscillation in time. So if I plot e to the I omega t as a function of time, I'm going to get an oscillation.
Yeah, e to the I omega t is cosine omega t plus I sine omega t,
If that helps.
if that helps at all.
So there's,
So see, you can get that oscillation frequency omega.
yeah.
Or with, yeah, with omega.
Does that answer your question?
Yeah.
Cool. Any last? Yes.
Does the derivative is having.
The derivative of the Fourier transform.
With respect.
With respect to time. Derivative of the Fourier transform with respect to time. So the derivative of the Fourier transform is a function of frequency. So you can kind of say like, if my Fourier transform is changing in time, that means my frequencies are changing. The frequency components of what I'm looking at has changed. So I don't know about derivative. I don't know about derivative. That's I guess part of the answer is, yeah, maybe the derivative matters in terms of changing, like, oh, how much am I increasing in this certain frequency over time? So as I wait and look at my laser, how much is it looking like exactly this frequency? The derivative might give you a mention of that, but I've never thought about it that deeply. Cool. How am I doing on time? What?
5 minutes and 6.
Sorry? 10 more minutes. Okay, cool. So I'll just say our oscillator is now complete. So this is our oscillator. Remember, so we still have a function of time. So it's oscillating over time. And in frequency space, so in energy space, it looks like this. So you can imagine now this is like kind of basically how the experiment works. If I have a nuclear transition, what does that look like in the frequency domain? Well, there's one frequency that excites it. So I'm going to represent that. So we're going to say this is the frequency domain. And I'm going to have my one nuclear transition be this line right here. And so my comb, my oscillator, in frequency space looks like this. It's got a bunch of lines. So if I were to put these on top of each other, you get kind of a picture of how the experiment works. Because what I can do is I can change the properties of my time to change properties of my frequency. And so I can move these lines. And if one of them hits this nuclear transition, so they line up, then you can actually see the excitation. So that's how we decided to look for this. So, back a few, 10 minutes ago, I said like, oh, it's about 100 terahertz uncertainty. If I want like a really good read on it, I can take my comb and I can scan it. And if I hit it right on, then I can see my nuclear transition. Oh, but yeah, by the way, for people who have not seen the Fourier transform, this is the video that brought me from not understanding Fourier transform to understanding a Fourier transform. It is miraculous how good this video is. And then Tian over there recommended this video, which also is kind of a pretty similar video. Kind of has the same picture of what's going on. But if you're going to continue on in physics or in engineering, or I guess anything STEM really, you'll want to know about the Fourier transform. And so I would implore you, so two takeaways from this talk: clocks are made up of oscillators and disciplines, and just learn the Fourier transform. And these videos are good at that. So our discipline is going to be this thorium-229 doped calcium fluoride. So remember, we only care about the nucleus here. So we're only looking at the nucleus. And so I can take my atom of thorium-229 and I can put it inside a crystal, and then I can excite it with a laser, and it'll work just fine. And so, we ask them for like a big piece of their crystal. It's big, 1 millimeter by 1 millimeter by 1 millimeter. And then said like, okay, this is doped with thorium, nucleus in this is nice and trapped. So we can just excite this with our laser and, scan over it and see if we can see the transition. So here's the experimental setup. Our laser comes from here. Can I do a laser pointer on this? All right, I guess not. A laser comes through this kind of hole right here. And you can see this tiny little crystal right here. It's not this big yellow thing, that's the crystal. It's the tiny little blue one. That's the thorium doped calcium chloride. And you can see the laser is actually going through it right now. This little white line right here. And then we terminate the beam right here. And so the kind of schematic of this is this. So I have my laser, my oscillator, the Fourier transform of the pulses, and I hit it on my calcium chloride crystal. And if my frequencies line up and I'm exciting my thorium nuclear transition, then I get all these little photons coming out of my crystal. I can collect those over here and count them. And if I see an abnormal amount of photons, then I can say I've excited. That's how we actually did it. Obviously, this talk is an oversimplification, but I need to thank a lot of people for the kind of infrastructure that kind of went into making us help making us so that we were able to do this experiment. So, I talked about like this comb. What's actually keeping it from like just going all the time? Well, a lot of stuff, but one is this really nice strontium laser that we have in our lab, and that is maintained by all of these people here. And so I guess these people and these people helped make our laser, helped make our laser. So we have to thank them. And it worked. So here is it working. Here's a selfie at 4 a.m. because we're so happy that it worked. There's a screenshot of me realizing we found it. And there's like some data as we're scanning through it. So this is kind of like, I'm supposed to do a day in the life of a grad student. This is possibly one of the most lucky things that I can imagine. Like everything really lining up, like lucky enough to get to work in a lab here, lucky enough to be in a good group, lucky enough to, while in that really good group, find this really cool thing and then like be there while it happened. It's nuts. So the Nature gave us a cover when we published it to them. There's me sleeping because I was tired. And then like after we found it, it was 2.5 weeks of like taking shifts, just scanning 24/7 because we were just totally going nuts about it. And I want to impress upon you that this is like the most lucky anomalous thing that you can really think of. Like Shankun over there spent like 7 years working really hard on the experiment just to see this, like working really hard. And he only got like 2 days of like the celebration. So as far as like life of a grad student, mostly it's being diligent and working hard every day. And then if you're lucky, you get to work with great people. And then if you're really lucky, you get to work with great people and find something cool about physics. So again, started with, oh, get that out of there. Started with, I'm probably the luckiest person on the planet. I continue to be lucky, even in college and grad school. We'd also like to thank, here's like their team, the homies that made it all happen. There's our PI, June. We got Tian, we got Shankun. Jake isn't here, there's me, and then Lars van der Wens was a great guy who like he was with us for a few years and helped us with the experiment and kind of kickstarted the kind of resurgent interest of this field. So we also have these crazy things that we have to give to the instrument shop. They actually make our experimental apparatus working. The electronic shop for like locking the laser, making sure it's not going all the time. CU Physics, we have to thank them because they scanned a bunch of stuff for us. CU Chemistry scanned a bunch of stuff for us. CU Radiation Safe to Office have been angels because we are not perfect human beings, and they forgive us for this and correct us and put us on the right path. So what next? Yeah, so you can make a really good clock. And you can make a clock just for clock purposes. There's reasons to do that. You can make a solid state clock, which is technically a little bit different, where you have like this big chunk of stuff, and you can imagine that, okay, if like for the atomic clock, there's a lot of stuff that goes into keeping your atoms in one place. The atoms are in one place if they're inside a crystal. They're just there. So you kind of remove a lot of that infrastructure and can make have the potential to make a smaller clock. This is my favorite part about it. And it kind of goes way, way back to the first few slides when they said, okay, what do these factors that influence the clock frequency depend upon? Like H bar, mu naught. How do those change over time? They shouldn't, but maybe they do. There's dark matter out there. There's a few theories as to why they would be changing. And the nuclear clock, since it's based on a totally different set of variables, so in the beginning, like I showed you atomic clocks, and they're dependent upon E naught, H, the proton number, and some other thing. They're all very defined by those constants. Nuclear clock is defined by a different set of constants. So you can actually compare the two and make a really good measurement of, is H bar changing? Is alpha changing? All these things that we take for granted as constants. And then, yeah, if you want to do quantum computing, sure, knock yourself out. Sensitivity and unity physics beyond the standard model. This is the good stuff. This is kind of, I'm sorry for showing such a complicated looking graph, like right at the end of the talk when things should be kept simple, but just ignore everything. Omega, but that dm, that's dark matter. And this lambda QCD, delta lambda QCD over lambda QCD, that's some quantum chromodynamic stuff. So that's what are the nucleons actually made of. But ignore all of this and kind of ignore that too. Think of this graph as a map. So what it's a map of is it's a map of places where dark matter can exist. And obviously it extends like farther down here and farther that way, because you can code up infinite theories. But there's a good reason that it stops here for this plot. And you can think of other clocks, so other clocks being like atomic clocks, have searched this area of the map. And they've said, I don't find any dark matter. This nuclear clock, you can see this line here. That means we get to rule out or find dark matter at this entire white space that's underneath the other clocks and above this yellow line. And if you do some improvements, you get this entire white space right here too. So that's kind of, the romance of it all, I guess, is, you get to see what if there's dark matter there? Like, what if there's like some new physics there? And that's, I guess, personally appealing to me. That's why, I'm so hyped up about this last slide. And this is the kind of outlook of what I'd like to encourage you to think about in the future. Dark matter. Thank you. I think I went way over. Not too bad. Okay.
All right, so thank you all for listening. If you have any feedback for us or for Jack, you can scan that QR code and leave some feedback. We're a few minutes past 6, so if folks have things to get to, you should go. But also, I'm sure Jack would be happy to take any questions that you are interested in asking.
Anything.
I'll just jump in and say, I have to steal my computer back in a few minutes.
Okay.
So if there's any questions that you need to like go back to the plot or something, ask them now.
Also, you can just come up here. Jack.
Yeah, I've got the slides on here. So if you want to talk in depth, I got time. Yes.
So, on one of the slides where you have the purple waves, right? So you were talking about how when the cone meets up with the spike from the experiment, you can measure the excitement. Is that because the driving frequency of the laser meets up with the natural frequency of the nucleus?
Yep, exactly. Yep.
Okay.
So the nucleus really, it's a discipline. I call it, because it only really cares about one frequency. And so when you're kind of saying like, oh, you know, I want to play the exact right note on the bass, you're listening for that one exact frequency. And this nuclear transition only listens to one exact frequency, only reacts to one exact frequency. And so that's why we're, you know, the energy of the photon of my oscillator lines up with the frequency that the discipline wants to see, and then you get excitations, and then you get
About the like a map kind of thing. Maybe put like what the first are having specific what looking for dark matter in for.
yeah, exactly. So when I said was kind of hinting at, you know, oh, you know, what if the fundamental constants like h bar, what if the fundamental constants like mu naught, what if the fundamental constants of alpha, if they're changing, we have no reason to believe they're changing right now. There's no good excuse except dark matter. So if I have, let's just say, a particle of dark matter, and it interacts with something in my nucleus, and h bar changes, then the frequency my discipline listens to has changed, and my laser will see that. And so that's kind of, you know, the broad overview and an experimental cycle of what looking for dark matter would be like. Yeah. I mean, ask a theorist, like there's a ton of different ways that it could change. And you can come up with a ton of different theories that could happen. And so there's reasonable limits. There's limits that, like, for example, our standard model. So our standard model of physics has some limits for where the frequency can, like, doesn't make sense afterwards. But I mean, it's up to theorists. You can, if you can cook up a particle, a way that the world works, and it spits out a, you know, a frequency, or, you know, like a particle, and it spits out something, then you should be able to maybe see it interact with nuclei more than you would see it interact with like these atomic energy levels. So the limits are whatever theory can cook up.
What's the QPN?
QPN limited clock is quantum projection noise limited clock. So as we said, there's kind of some certain limits to how good a clock you can make. Quantum projection noise is pretty complicated, but it's I'll say quantum limit to the clock. Is that a quantum?
So can they,
Sorry, what's up?
is that doesn't
Does, sorry, what?
we don't yet have a quantum projection noise.
No, we don't, yeah.
Have you been limited to the clock, or if you get limited to time?
Good question. I don't know.
Or is it just like energy, time, uncertainty?
Yeah, I don't know. I just don't know. I'm sorry.
Any questions?
So once you have, oh, sorry, you can.
I just,
Yeah. No, you good.
I was just gonna ask, why is the other clock, like, the cutoff for that, so just like consistent, like fluctuating? This blue area, Yeah.
it's because this is like the cumulative work of many thousands of scientists. And so each scientist can say like, okay, I'm gonna look at this area. I'm gonna look at this area. So you're kind of like looking over this map and you're mapping out, like each scientist is looking at each individual little area and saying like, okay, I can confidently speak on this area that there's nothing. And the kind of cumulative work of all those thousands of scientists is, you know, the fact that it's not. Yeah. It also extends up there. Like we definitely know it's not oscillating at those higher frequencies, but as science gets better, as people measure more accurately, you kind of go down to these little limits. And that's why it's kind of, zigzaggy. And so a theorist can come along and say like, okay, your good lord, your nuclear clock about here. And then we'll do the experiment and we'll say, I can confidently speak on like, and then I don't know. That depends on how the experiment ends up coming out.
Yes. How do you sort of relate this clock now back to your like super nice drawing?
Yeah, so this clock is actually referenced to this clock is actually referenced to the Strongian clock. So if I have my comb in the mid IR and I do high harmonic generation, then I get my VUV comb. To kind of control the properties of my VUV comb, which is the one exciting the nucleus over here, I can actually control my properties of this one before it goes through the higher harmonic generation. So, and then this comb is determined by the Strongian clock. So my IR comb stability is tied to this super stable clock here. And then I do 7th harmonic generation. And so I get kind of like a collective behavior between my two combs. And so I can confidently say, I can read out my thorium transition, which is over here, just by changing my comb on my IR side.
See you in 2 weeks.
Thanks.
Weather.
Oh, yes, sorry, you were with that.
It was.
All right.